Uh, Hello everyone. Hello Astrolabos. Good to see you. Good to have you here. I'm sorry that today has not been a good day for you, but I hope that your luck gets better. Well, at least I have some psych stats around the day on the good note. Yeah, I will do my absolute best if my voice doesn't give out. I've done I haven't gone a day for a while without talking for at least an hour straight. So my voice is struggling. Or no, for at least 2 hours straight, I think. Or like an hour and a half straight. I haven't gone a day since last week without yapping for a very long time, and I don't talk much outside of lecture and stream, so it's doing horrible things to my vocal cords, but we persevere for the sake of science and stuff. I don't know how many people here are aware, but I'm a social psychologist. I think I've mentioned this before, and starting actually I think it started today for the online pre-conferences, the biggest social psychology conference I think in America for sure. I'm not sure about the world, but it's starting today, and I can't be there, so expect me to be super obnoxious, retweeting and commenting on as much research I see as I can. I wish I could go, but it's not always possible. I gotta save money, and it's hard to get away in the middle of the semester, which stinks. But SPSP, keep an eye out. There's gonna be some cool work being presented. But for now, it is my job. Oh no. Oh, I was wondering about the sudden uptick in retweets. Yeah. The big conference of the year is happening, and I'm very, very excited about it. I'm hoping that I haven't seen anything from it quite yet, but there's these things called pre-conferences that happen before the conference. So the conference technically starts on Friday, which is when all the big stuff is going to get started. But there's mini conferences today and Thursday called pre-conferences. And my favorite pre-conference, I think, is happening tomorrow. And I don't know if I know anyone who's going, but it's the Technology and Media pre-conference. And I'm hoping I can get my grubby paws on at least figures from it, or people's posters or something like that from them posting them on social media. Or, posting them on the Open Science Framework or something. I really want to see as much as I possibly can of it, even if I can't make it. But yeah, there's gonna be a lot of retweets from me probably through the weekend. I think the last day of SPSP is Saturday. So through the end of the day Saturday, my Twitter is going to be insufferable. I'm going to be sharing all the cool science that I spot, and I'm very excited to see what's going on there today. I have some friends who are presenting, but of course, they're doing some really cool stuff too. And I'm very excited for them. And I've told them that if Sona Systems is this company that helps run participant pools on college campuses. A lot of colleges will have this thing where they have intro to psychology students. They give them the option to participate in studies for part of their grade, and they can do other things if they don't want to do that, but it's an option. And the system that a lot of schools use to manage that is called Sona. And Sona last year at SPSB was giving out Sona themed kazoos. I think I posted a picture of it on Twitter, but I asked one of my friends if they have them this year, can she pick it up? Can she pick up a kazoo for me and bring it back? So I will report back on whether I acquire my Sona Systems kazoo. Sai has also told me Qualtrics, which is the service that a lot of social psychologists use to create surveys. Apparently they have Qualtrics branded socks, but those are only for employees, which kind of sucks. But anyway, right, let's talk about it. I wish them luck in their mission. Me too. Me too. I should actually probably tell more people just in case. Oh, hello, Water Knight. I'm lurking on my way to work, y'all. Good luck with the stream. Thank you. I suppose we should probably get to it, right? We should probably start on the stream. Oh, Mr. Kibby's kind of restless today, so I probably shouldn't drag things out unnecessarily, lest he destroys something. He's very much in playful mode right now, so hopefully he doesn't attack me in the middle of the stream. He's very cute though. Okay, so last time we talked about ANOVA. So here we go. ANOVAs are tests that we do when? When do we use ANOVAs instead of t-tests? When would I conduct an ANOVA rather than a t-test? When we're comparing 3 or more sample groups. Exactly. If we have 3 or more conditions or 3 or more samples and we want to compare them, ANOVA is our choice. Great job. I don't want to put like too much on y'all. So I'm going to kind of like just review these questions. I'm not going to ask y'all all of them because that's a lot in a row. But the next one, in ANOVA, we take all of the variability, all of the variance in the scores on our dependent variable and split it into 2 parts. The first thing is, of course, what are those parts called? And we actually went over this. We had this as a review question at the end of last time, too. Those 2 parts are the between treatments variance, which is the variability between your conditions, and the within treatments variance, which is the variability within each condition. The between treatments variance estimates the effect of your independent variable with some error in there, and the within treatments variance is your estimate of sampling error. How are they used in the F ratio? Well, you take the between treatments variance and divide it by the within treatments variance. So the effect of your independent variable plus some error divided by error to kind of get a ratio of how much bigger your effect is than error. That's kind of the goal of the F ratio. That's why it's called the F ratio. It's a ratio of one type of variance to another. Oh my gosh, this cat is very excited. Mr. Kitty, would you like to answer in ANOVA what the expected value on average for the F ratio is if we fail to reject the null? What do you think, Mr. Kitty? He gave me 1 meow, and that is correct. If we fail to reject the null, on average, the F value should be 1. Good job, Mr. Kitty. Mr. Kitty knows about that. Why would you put him on the spot like this? He did well, though. He did great. You need to understand, Maury. Mr. Kitty has sat through this lecture at least 3 times between me teaching online. Well, never mind. He knows exactly. He knows his stuff. He's taken this class 3 times minimum. So he's very good. He knows his stuff. He's a good boy right there. Then there's the matter of what can we expect the F value to be on average if we do reject the null? Hey guy, I failed to reject the null. So much negations in this sense. I know, it's horrible. But unfortunately, we have to say fail to reject the null. We can't say we accept the null because the type of statistics that we're doing, we cannot test if 2 things are the same. So we can't accept the null because that implies that our conditions are the same. But we can't test for that. We're just seeing if they're different. So we can't conclude that they're the same, so we have to use this weird, annoying fail to reject the null language instead of saying we accept the null. Because we didn't test if the null was true. We just don't have enough evidence to say that it's false, you know? It's annoying, but it is what it is. So if we reject the null hypothesis, our F value is going to be greater than 1, because treatment plus error, if our independent variable does something, then the variance due to our independent variable should be a much bigger than error. You're dividing a bigger number by a smaller number, you're going to get a value bigger than 1. It's like in Russian, where double negatives still equal a negative statement. Oh, I guess it's kind of like that. Fail to reject. We have not disproved the null. Not that we can prove anything with stats, so disprove isn't quite the right word, but yeah, it's 2 negatives to express a negative, which is like I know why it's phrased that way. I know why we can't phrase it in a better way. I guess we could say we don't have enough evidence to reject the null. I don't know if that makes it any better, actually. We can't reject the null. I've heard people say we retain the null, which is a bit less wordy. Yeah. We have to keep going with the null. Or something like that. Or I don't know. I don't know. I'm not terribly good with words, to be honest. All right, last one. Eta squared. Eta squared was the effect size that we learned for ANOVA. Hey, Harday. No null left behind. Yeah, kind of. I feel like it's mostly semantics. I've heard less accurate science terms. That's true. A lot of the ways that we talk about statistics, it's that like semantic thing where like we have to be very precise with our language because we don't want to cause misunderstandings. But at the end of the day, it's just, it can be a bit of a headache. Like, I don't know. But anyway, eta squared. Eta squared was the effect size, and eta squared was trying to be like r squared. It was trying to tell us the proportion of variability in the dependent variable that can be explained by the independent variable. So sort of like, if I knew which condition you were in, how accurately can I predict your score on the dependent variable? It's kind of along those lines. The problem with eta squared is that it's not doing it very accurately. It tends to overestimate the true effect size. So it'll give you a number that represents how big of an impact your independent variable had, but the number's going to be pretty consistently bigger than it should be. Unfortunate. So that's what we did last time. Now, last time I mentioned, when we reject the null for an ANOVA, that doesn't necessarily mean that we know what's going on. It just told us that there is at least one difference somewhere in there. It didn't tell us how many of the conditions are different from one another. It didn't tell us which conditions are different from which other conditions. So our goal today is to try and cope with that. Our goal today is to try and figure out, okay, you've rejected the null on your ANOVA. Now what? Now what are you going to do? How do you figure out where the differences are? You know they're there. But how do you look for them? So just to refresh you on the example that we were using last time, this was, does how the teacher is presented, does that affect learning? So we randomly assigned 15 people to take a stats class. 5 people took the stats class with no visual of their teacher. 5 took it with a live action video of a teacher, and 5 took it with a VTuber model as their teacher. And then we had them take a stats quiz at the end, and we saw how many problems they got right out of 10. And this was our data. And I know, yeah, once again, I set up, so you Captain America. So you've rejected the null of your ANOVA. I do not remember what tone of voice he says that in at all. But yeah. If you have done that, here's what you do next. These are the next steps. I feel like that's kind of, I'm trying to do like the corporate training voice. If you rejected ANOVA, the null of your ANOVA, there are some steps that you will need to take. Here are the next steps if you reject the null of an ANOVA. Or something, I don't know. Yeah, I tried my best. I tried really hard. So here's the data that we had. And here was the ANOVA that we calculated. We got an F value of 11.28. So we rejected the null. We did find that there was some difference between our groups, that the visual that people had during this lesson did predict differences in their scores. But we don't know which groups were actually, like had higher scores or lower scores. Like we can look at the means here and say, it looks like the live action video had the best results, but we don't know if these differences are significant. We can't be sure. So that's our goal. Now, to figure out where those differences are going to be, we are going to have to compare all 3 groups to all 3 other groups. We're going to, every group to every other group, which means comparing the no video to the live action video, the scores in the live action video to the VTuber video, and the scores in the no video to VTuber video. We're going to compare every condition to every other condition, which is going to be a lot. So how do we compare them? Well, this is a problem that people have been faced with in the past, and I have a meme. So, your ANOVA is significant, or in this case, we have a bunch of t-tests that are significant, but just imagine that says ANOVA. We have an ANOVA that's significant. How do we control for type 1 error? So how do we prevent getting a false positive when we're conducting these follow-up tests, when we're following up on this ANOVA? This first suggestion, control for at least one type 1 error, which would be alpha 0.05, which is not super effective. That's just like, that only works if you're doing a single test, like one t-test. Here we have use linear contrasts, which I'm going to use a slightly different name to refer to them in this lecture. I'm going to call them planned contrasts, but we're going to go over that. And then this guy on the right, this is Bonferroni, he's a statistician. Divide your alpha level, in psychology, usually 0.05, by the number of comparisons. It's the number of tests you're doing. People don't really like the Bonferroni correction. I like the Bonferroni correction, but a lot of people don't like it. So I'm not going to talk about that now. We're going to talk about the Bonferroni correction when we talk about the repeated measures t-test. But you could use, the repeated measures ANOVA, but you could theoretically use a Bonferroni correction to follow up just the one way between subjects ANOVA that we're talking about this week. But I'm not going to get into that this week yet. All right, so let's talk about those planned contrasts, those contrasts foreshadowed in that comic. You should only ever use planned contrasts when you have a very strong hypothesis. You have a very clear idea of the results you're expecting. They're called planned contrasts because you plan to do them in advance. You have an expectation that your ANOVA is going to be significant, and you have a very strong expectation of what you're going to find. So let's say I was very, very confident that clearly VTubers are the best educators. Out of this group, I had a very clear hypothesis that the VTuber group would have the highest mean. That would be a strong hypothesis. Or let's say I thought any type of visual, whether it's live action or VTuber, would result in a better outcome than no video. That would also be considered a strong hypothesis because I have a clear expectation of what my results are going to be. If I have a hypothesis like that going in, I can do a planned contrast. What should I do if I encounter a GENOVA test? What material should I equip? What material should I equip? Unfortunately, that is, I have not gone to the University of Final Fantasy. I have never encountered any metaphorical or literal one-winged angels. This is outside of my area of expertise. I do have a friend, though, who I think has a very advanced degree in that franchise, who I could probably ask. Unfortunately, I don't think he's online right now. So sorry, Marlon, but happy to have you here. Oh, no. Hello. Hello, welcome everything with Jim. We're talking about how to follow up an ANOVA. So I am Mylan. I'm Mylan. I do videos on psychology and statistics, and today we're going through an introductory statistics course, and we've just talked about ANOVAs, where you can compare 3 or more conditions to one another. Now we're talking about following up the ANOVA. All right, so you have to have a strong hypothesis to do these. You need to make sure that you have an idea of what's going to happen next. And planned contrasts are actually really similar to the overall ANOVA. They also test hypotheses using an F ratio. So the variance between the treatments divided by the variance within the treatments. They're using that same logic. They're just tweaking it a little bit. And by tweaking it, I mean planned contrasts are basically just doing an ANOVA with only the 2 groups you're currently comparing. So let's say I wanted to compare the no video condition to the live action condition to see if those 2 means are different. I would calculate the between group variance the same way we did for the original ANOVA, right? Like calling your shot. Hey, Phi, good to see you, Phi. I hope you're doing well. But yeah, pretty much like calling your shot. Yeah, like you have a strong idea of what's going to happen, and maybe that's not what you find. But the idea is, yeah, you should be looking for something in particular. You should know what you're looking for. It's the stats version of pre-registration. Kinda. Like the idea with pre-registration, so if you're unfamiliar, if you haven't heard Psy's great explanation of pre-registration is writing down what your entire study is going to be, what your hypothesis is going to be, all of that stuff before you collect even a bit of data. And then, I'm sorry, Jim, I'm not a clinical psychologist, and I'm not qualified to discuss individuals' mental health. So I can, even academically, I'm not qualified to talk about bipolar. I'm sorry. Anyway, yeah, so pre-registration, you're writing down your entire plan. Yeah, okay, cool, yeah. Sorry. Thank you for asking, though. I do appreciate that you would ask. All right, yeah. So pre-registration, you write down your entire plan before you do it, and then you post it on the internet and lock it so you can't edit it. That way, everybody knows what you're gonna do before you do it. You would, if you are planning to do plan contrasts, you could tell people that in a pre-registration document. Part of that would be you would pre-register exactly what your hypothesis is and what type of test, plan contrast or the other ones we're going to talk about, that you would use to test that. And then you would say exactly how you're going to do the plan contrasts. And that gets more important if you have more than one independent variable. But yeah, this is... typically, you'd only do this if you have a hypothesis, and with pre-registration, I feel like you can almost like extra justify doing this. So, same process. You calculate the between treatments variance using exactly the same formula as we did for the overall ANOVA. You calculate the grand mean, which is the mean of the two conditions you care about. So in this case, mean of condition 1 is 1, mean of condition 2 is 4, 1 plus 4 is 5, divide by 2, the grand mean is 2.5. The mean of our means is 2.5. Then you can calculate the sum of squares between using the same formula as before. You calculate the sum of squares of your two means, multiply it by the number of people in a single condition, which in our case we had 5 people in each condition. So multiply that sum of squares by 5, and you get your sum of squares between of 22.5. So you do that. You also have to calculate a new degrees of freedom. Before we were comparing 3 groups, so our degrees of freedom between was 3 groups minus 1 or 2. In this case, though, I'm only comparing one group to one other group. I'm comparing 2 groups. So the number of groups I have is 2 minus 1 gives us a new degrees of freedom of just 1. And then we use our new sum of squares and our new degrees of freedom to calculate a new variance between treatments. So this is the variance only between these two conditions. Still same formula, sum of squares between divided by sum of squares within. So in this case, sum of squares between is 22.5 divided by sum of squares within, 1. 22.5 divided by 1, our sum of squares between, our variance between these conditions is 22.5. So that's what you do, and that's the bulk of the work for a plan contrast. You calculate the sum of squares between and the degrees of freedom between to get the variance between only the two conditions you're comparing. And then after that, you're almost done. We do not have to recalculate the within treatments variance. We don't have to recalculate our estimate of sampling error here. Isn't that nice? Why? Like, it's nice that we don't have to do any extra work here. It's nice that we don't have to recalculate our error term. But does anyone want to guess why it's not only just efficient to not recalculate your error term, but also better to not bother recalculating it for only the two groups? Why do we want to keep the original error term? I'm willing to offer hints as well, by the way. Less risk of human errors or source of computing bias. You're close. You're getting closer. Or that's definitely along those lines, guy. Good job. Yeah. So I'm gonna give you a hint to get you a little closer. The original ANOVA calculated the original ANOVA, it retains the selection error from the other sample, so it's likely to be a more accurate measure of error. I didn't even need to give you the hint. Astrologopose, you've got it. You were close. Astrologopose pulled you all over the finish line. Exactly. The idea here is that in the original ANOVA, we had 3 conditions. And we had 5 people for conditions. That estimate of error from the original ANOVA is based on 15 people. In this one, we only have 10 people because we only have 2 of the 3 conditions. So if we recalculated our within treatments variance, if we re-estimated our error, it would be based on less data and it would be less accurate. The more information we have, the better. So we don't want to recalculate it. One, it's more work to recalculate it. And two, even if we did that extra work to recalculate it using only these two means, we're losing valuable information by doing that. So it is actually worse to do more work in this context because you're losing information. Your estimate of sampling error would be less accurate because it's based on less information. Isn't it nice when being lazy is totally justified? I love it when that happens. It's rare. But in this case, it's better and more accurate to be lazy than it is to go the extra mile. So we can just take the variance within from the original ANOVA, don't need to recalculate it, just use that one over again. So once we've done that, we take our new variance between conditions, that only is the variance between the two conditions we're comparing, divide by the old variance within conditions, because that's a better estimate of error, and that gives us our new F value. Our new F value, just comparing the no video and the live action video conditions, is 16.92. Nice. Then, of course, we have new degrees of freedom, right? We recalculated the degrees of freedom between. It used to be 2, now it's 1. This means we're going to have to look up a new F critical value. So for the planned contrast, you will need to go back to the F table, and you're going to need to use the degrees of freedom, the new degrees of freedom between 1. The degrees of freedom within the 12 is going to stay the same. We're keeping that. But we're changing the degrees of freedom between to reflect that we're only comparing 2 groups instead of 3 groups. So you're going to get a new critical value. In this case, degrees of freedom between of 1 and degrees of freedom within of 12. Alpha of 0.05 gives you a critical value of 4.75. So to reject the null, your F value needs to be bigger than 4.75. Do we reject or fail to reject the null based on this F value? Correct. We reject the null. Our F value is bigger than our cutoff. 16.92 is bigger than 4.75. Therefore, we reject the null. We conclude that these two conditions are different. We have done our planned contrasts. We reject the null, and now we can just look at the means of our two conditions to see which one people did better in. So if we go back here, now we know that the no visual and the live action conditions are significantly different from one another. We've done the planned contrast. We can see the mean of the no visual condition, people who had no visual on the teacher, and the mean of the is lower than the mean of the live action condition. And because we've rejected the null, we've concluded that difference is bigger than sampling error. We can conclude that people who had the live action video of the teacher scored better on the quiz than people who had no visual of the teacher. That's a planned contrast. If you want to calculate the effect size for like that specific for that specific contrast, you can calculate eta squared for this as well. You take your new sum of squares between that you calculated for only those two groups, divide by the original sum of squares total from the original ANOVA. So we can recalculate our sum of squares between for just these two groups as 22.5. We divide it from the original sum of squares from the total from the original ANOVA, 46. So let me find us our original ANOVA table again. Yeah, there. Sum of squares total of 46. And that will get you your effect size. In this case, 0.49. About 49% of the variability in scores can be explained by whether people had a live action video or no video. Of course, this is eta squared, so this 0.49 is probably overestimating the actual difference. But, you know, like I said, eta squared is the easiest one to calculate, so kind of like... That's the one I'm talking about here. But there are better, less biased effect sizes for ANOVA out there. Now, let's say you want to write this up in APA style. Here's an example write-up. We've got people with the live action image, or I guess the live action video, solve significantly more stats problems, I guess correctly, I should say, with a mean of 4 and a standard deviation of 1.2. 2, compared to people with no visual representation of the teacher, mean of 1, standard deviation of 1.22, comma, this was an F test. This was ANOVA, which is an F test, which uses the F distribution. So F, on 1 and 12 degrees of freedom, because those are the degrees of freedom we use to look up our critical value. That value we calculated was 16.92. We rejected the null, so p is less than 0.05. The probability that we would have randomly selected two samples with a difference this big if the null was true is less than 5%. And eta squared is 0.49. A slight overestimate of the true effect size is 49% of the variability can be explained by the condition that they were in. There's your APA write-up. You got I tell you the independent variable, it was they were either live action or no visual. I tell you the dependent variable, how many stats problems they managed to solve correctly. And I tell you which condition had a higher mean. The live action solved significantly more. And then as a bonus, I also give you the mean and standard deviation of each condition. So if you do want to check to make sure I interpreted that correctly, you can go ahead and do that. How we doing? Everything making sense, or anything I can clarify? Following? Awesome. Glad to hear it. Mr. Kitty's asleep. We have time. He's taking a nap. All right, we still got a bit more to go. But I think we're over halfway through, so that's nice. Okay. So that's your first way of following up an ANOVA. Plan contrast, but you should only do them if you have a clear hypothesis. You have a strong expectation for what you're going to find. They might not end up confirming your hypothesis, but you should only do them if you have a hypothesis, is the idea. All right. So before I get into the next two ways of following up a significant ANOVA, I'm going to do a little bit of review of something that we talked about last time. The reason why we do an ANOVA instead of a bunch of t-tests is because, well, one t-test is fine. One t-test is fine. Your chance of getting a false positive on a one t-test with a 2/3 through the slides even. You're better at math than me, Astrologipos. Thank you very much. So yeah, you have, with an alpha of 0.05 for one t-test, you only have a 5% chance of making a false positive, roughly. This is your test-wise alpha. But of course, as we established last time, if you do more than one t-test, that chance of making a type 1 error is going to go up. Which means the more tests you do, the higher the probability you're going to make a type 1 error somewhere. Your total probability of making a type 1 error across your entire study is called your family-wise or experiment-wise alpha. Yeah, it's not quite like a multiplicative increase in type 1 error rate, because like to some extent, you're still working with the same data, and you've still got the same variability, but it increases it, but not to the point where it's like a full 15% type 1 error rate. It doesn't go up that high, but yeah, Marlon's got the right idea. It's definitely going up higher than we would want it. We don't want to make a type 1 error. We don't want false positives. So, ways to avoid a type 1 error. I swear, this is going somewhere. Well, first, conduct an ANOVA. Rather than just jumping to t-tests, conduct an ANOVA. The ANOVA only has a 5% chance of a type 1 error. If your ANOVA is not significant, you stop. You do not go any further. If your overall ANOVA is not significant, it's already told you, with that 5% chance, that there is nothing here and you shouldn't go digging. If you go digging anyway, you're increasing your chance of a type 1 error because it's already told you there's nothing there. So if you find anything beyond that, it could very well be a type 1 error. So if your ANOVA is not significant, stop. Don't do anything else. It's one test that tells you there's no difference before you start doing those additional tests that could potentially raise your type 1 error rate. It's a gatekeeper, essentially. You can only go on and do more tests after we've made sure that it wouldn't increase your family-wise alpha, or your family-wise error to do it. Or at least we're more certain this won't increase your family-wise error because we've done this with that proper alpha level, as opposed to just going straight into 3 t-tests. If you do reject the null on the ANOVA, then you can go forward. So if you do reject the null on the ANOVA, Your first option, of course, is planned contrasts. But that only works if you have a strong hypothesis. And honestly, most of the time you will have a strong hypothesis. Most of the time you're doing a study, you should have a pretty clear idea of what you're expecting. You'll have like read a lot of the literature, you've seen what people have done in the past, you've probably got a strong theory that you're working off of that makes a very specific prediction about what you're going to find. But sometimes you're doing exploratory work. Sometimes, if you're like me, I analyze data for fun, just to see what happens sometimes. Sometimes you're doing this without a hypothesis. If you have an ANOVA that is significant and you don't have any reason to expect there should be differences there, in other words, if I'm doing an ANOVA just for the heck of it, I have no reason to expect that these groups should be different from one another. I'm just messing around with the data and doing exploratory stuff. Then you got to be a bit more careful. You can do planned contrasts if you have a hypothesis because you're expecting something to be there. So it shouldn't be as surprising or as unlikely for something to be there. In other words, we're not as worried about a type 1 error with planned contrasts because we were expecting to find something. We have strong reasons to think that there's something there. But if you don't have a hypothesis, you don't have strong reasons to think that something's there. You got to be more careful about making a type 1 error because you're not expecting anything. So if you don't have a hypothesis, or maybe you just want to be extra cautious, which honestly, these days in psychology, most people skip the planned contrast and just go straight to the post hoc test just out of an abundance of caution. So it used to be if you had a hypothesis, you'd be doing a planned contrast. These days, even if you have a hypothesis, you might want to do these post hoc tests anyway, just to be extra sure you're not getting a false positive. Because these post hoc tests they're more conservative than planned contrast. They're more careful. It's harder to reject the null on them, so you're less likely to get a false positive out of these guys, which is why we like to use them a lot. Technically, they're meant for if you don't have a hypothesis, but you can also do them if you do have a hypothesis, just to be careful, you know? And that's what I do, honestly. Like, even if I have a very strong hypothesis, I will still do post hoc tests instead of planned contrast, just to be extra sure, you know? Better safe than sorry kind of deal. So, what are post hoc tests? Post hoc tests are more careful about experiment-wise error. They're more conservative, they make it harder to reject the null. They have adjusted the way you're testing for significance to make it harder to reject the null, to reduce your chances of making a type 1 error, and to reduce your overall experiment-wise error, your overall probability of making a type 1 error. The two most common types of post hoc tests that we're going to be talking about today are Scheffé and Tukey. Both of these are more conservative than planned contrast, so both of them make it harder to reject the null than a planned contrast. In other words, you're less likely to get a type 1 error than with a planned contrast. But that doesn't mean they're equal. Scheffé is a bit more conservative than Tukey. It's harder to reject the null with a Scheffé test than it is with a Tukey test. So let's start with Scheffé. And I'm going to start with the Scheffé test mainly because it's actually really, really similar to planned contrasts. It only has one difference from planned contrasts, which ends up making a pretty big impact on the results. But like, it's a really small tweak, and so it feels like a natural way to follow from planned contrasts. For a planned contrast, very similar, for a Scheffé test, it's very similar to a planned contrast. You recalculate the sum of squares between using only the two groups you're comparing, just like we did with planned contrast, but you don't change the degrees of freedom. The planned contrast recalculated the sum of squares between and then used degrees of freedom that reflected comparing only two groups. This recalculates the sum of squares between but uses the original degrees of freedom based on the original numbers of groups. So for planned contrast, we were dividing our new sum of squares between by 1. Here we're dividing our new sum of squares between by 2. Then you compute the F as per usual. You use your new variance between treatments that you calculated divided by the old variance within treatments. So actually you don't have to do even as much work here. And then you compare your new F value from the Scheffé test to the original critical value from the original ANOVA. So this is actually an even lazier version than the planned contrast because you're not swapping out the degrees of freedom and your critical value doesn't change. but it makes sure that your F value is going to be at least half as big as it would have been in a planned contrast. And of course, smaller F values, less likely to be past your critical value. It makes it harder for you to reject the null. That's a Scheffé test. It's saying we're going to test for a difference between these two groups, but we're going to make it harder for us to find a difference, just to be extra sure that if we do find one, it's probably real. So let's say I was doing the same thing as before. I'm comparing they have no video to the live action video conditions. I recalculate my sum of squares between, and I get 22.5. Here's the variability between the two conditions that we calculated with the planned contrast. So we had the new sum of squares between divided by the new degrees of freedom, and we got an MS between, a variance between our conditions of 22.5. With the Scheffé correction, we still have the new variance between conditions, the 22.5, but we're dividing it by the old degrees of freedom too. So our variance between conditions in Scheffé is half as big as the variance between conditions in a planned contrast. And because the variance between conditions is the top of your F value, the numerator of your F value, that means your F value ends up being smaller. So here's the F value that we got for the Scheffé test, 8.46. Let's compare that to the F value that we got from the planned contrast. The F value that we got from the planned contrast was 16.92, right? So the F value that we get from the Scheffé is half as big as the F value that we got from the planned contrast. It's harder to reject the null because it's going to give you a smaller F value. That's the idea here. We would still end up rejecting the null. The original F critical from the original ANOVA is 3.89. So our F value for the Scheffé test is still bigger than the critical value. We still reject the null, just like with the planned contrast. We still find there's a significant difference between those groups, but it's a bit of a closer call than it was before. Our F value isn't quite as much bigger than the critical value as it was with the planned contrast. That's a Scheffé test. You're testing between differences between two groups, but it's making it a bit harder to find one. How we doing on Scheffé? We feeling okay? I hope so. Gosh, how far in are we? Because my voice is feeling really tenuous right now. We're 21. No, I don't actually know where we are. My voice is feeling weird though. Seems good? Awesome. Like maybe 40 minutes in? Is that how far we are? Sounds like it can get a lot tougher than a planned contrast. Yeah, especially if you have more than 3 groups. Like if you have 4 or 5 or 6 groups, that F value will start shrinking real fast. The more groups that you're going to be comparing. And that makes sense because like the more groups you have, the more comparisons you're going to do, which means the higher your family-wise error rate. So it's gotta be really harsh on your F value to make sure that your family-wise error rate doesn't go up too high. Good observation here today. Astrologic was 18 out of 21, so 6 out of 7. The simplified version of 18 out of 21 would be 6 out of 7. Yeah, we only have 3 slides left. We're almost there, which means now I get to talk about the Tukey test. Tukey is such a fun name to say, by the way. I highly recommend just saying Tukey to yourself because it's fun. It's just delightful. It brings joy to my heart. And don't we all need joy to our hearts? In our hearts from time to time. For me, I'm just going to say Tukey, Tukey, Tukey. I'm going to say Tukey a lot. It's going to be great. Anyway, Tukey test, not turkey test. A lot of my students will accidentally, especially if I teach this in the fall, because fun names are great. I love murmuring Schrodinger as I work. Yeah. I've been collecting a list of fun psychologist names. I think I lost the original list that I had, but Tanuki is a Tanuki test. That's a new one. I haven't heard Tanuki test. But yeah, when I teach this in the fall semester, I'm usually teaching about Tukey tests towards the end of November. And here in America, towards the end of November means it's Thanksgiving. And what do Americans traditionally eat on Thanksgiving? Turkeys. So I will constantly get my students calling this a turkey test, and like I'll give an exam, and one of the answers might, like some semesters, one of the answers is Tukey test. And the amount of students I have that write down turkey test is kind of ridiculous. And like I give them full points. I'm not gonna lie, they knew what they were talking about. They just added an extra R to the word. So like I'm not gonna blame them. I'm not Tukey. I don't care if they misspell the name. It's honestly kind of funny. I like Tanuki test though. Maybe we should come up with like little mascot characters for all these different types of tests, and the Tuki test will have some horrible combination between a turkey and a tanuki. Or tanuki. I'm so bad at figuring out which syllable to emphasize in Japanese words. I think theoretically there shouldn't be syllabic emphasis. I don't remember. It's been a while. But I don't know how to say words without emphasizing at least one of the syllables. I need to practice. Anyway, let's talk about the Tukey test. So my voice doesn't die before we get through this lecture. The Tukey test is a way to compare the means of two groups. I guess Tanuki or Tanuki is a better way to write it. Yeah, could be. I don't know, but it's a little one. They're so cute. They're so cute. I want a pet. I want a pet one. Maybe when I go to Japan, I can go... Do you think they have tanuki in the zoo at Japan? Or would that just be, like, kind of weird? Because, like, I don't know. Animal critter. I'm so distracted by fluffy animals. It's a very good thing Mr. Kitty is taking his nap. Okay, right. So you can use this to compare two means, which is basically what the planned contrast and Scheffé test were also doing. You compare two means, but this does things a little differently than the other two. In fact, it does things differently than basically anything else that we've done in this series of lectures. So first off, it's not just called a Tukey test, it's called Tukey's HSD. Anyone want to guess what HSD stands for? I'll give you a hint. It's snarky. Tukey was being snarky when he named this. Standard deviance. Not quite. Let's get one or two more guesses. I want to see what y'all think before I tell you. Highly specific determination. Hugely stupid. Oh my gosh. So HSD stands for honestly significant difference. The implication, of course, being that other ways of testing for a difference between two groups are not quite honest. They aren't good. They aren't as good as Tukey's method. I could be wrong. This could just be some sort of like Psych stats urban legend. But it's my understanding that Tukey didn't like the other ways of doing it, and he named this the honestly significant difference test as a way of throwing shade at the other people who tried to come up with solutions to this problem. That could be wrong. It could just be like sort of like an urban legend, but I think it's funny. And adding the honestly in front of honestly significant difference does kind of imply that there is a little negative emotion going into at least the naming of this test and probably its creation. Anyway, up until this point, pretty much all the significant tests we've been calculating something like a Z or a T or an F value and then comparing it to some sort of benchmark on a distribution and using that to determine if two means are different. This is a lot more straightforward, actually. Which is, ironically, I think makes it harder because we're so used now to using, like, critical values and things like that. The test versus the test she tells you not to worry about. Exactly. Scheffé is, like, shoving Tukey in a locker, like, don't look! Okay. So what Tukey does is Tukey spits out a number. Tukey's gonna spit out a number that is the minimum difference between two means that Tukey would consider significant. So all the other tests are like, this is the minimum distance between one mean and another mean in units of standard error that we would consider significant, or the minimum ratio of signal to noise that we would consider meaningful. Tukey's like, screw that. I'm just gonna come up with like the minimum numeric difference between two means and call it a day. Like 4 problems versus 1 problem. I think a difference of 2 problems, if the difference is more than 2, then that 1 and 4 are different. You know, like that kind of thing. It's like a much simpler way of thinking. You don't have to think about like distributions and stuff like that quite as much. You're just comparing one number to another number and seeing if the difference between those 2 numbers is bigger than the HSD value. That's all. So, the original version of the Tukey test could only be used if you had an equal number of people in both the conditions you were comparing. That's not true anymore. They've found ways around this. So like if you do have unequal sample sizes and conditions, you can still do a Tukey test with the updated version. And like if you do a Tukey test in R, it will use that updated version. But the original version that you calculate by hand that I've got in this lecture should only be used if your sample sizes in each condition are equal. Which, you know, doesn't happen that often in the real world, at least in social science, because, you know, participants will drop out, or people in one condition or another will have bad data, or whatever the reason. But here's the formula. The honestly significant difference value, the HSD value, is equal to Q, which is a new letter. Don't wonder if you've seen that before. You haven't, unless you've taken something with Tukey before, I think. Q times the square root of your error term divided by your sample size. And this is why originally it could only be done if you had equal sample sizes in each condition, because it assumes that the number of people you have in each condition is equal in the formula. Q, that new number, is a number that allows you to incorporate your alpha level in there. So it's a table, you go to the Q table, you look up your Q value, and that's how you incorporate that alpha 0.05 in there. So it's kind of taking the place of an F or a T table a little bit, but it's not directly giving you a critical value. It's just giving a number that you would plug into this formula. The MSW, again, that's your variance within from the original ANOVA. Little n is the number of participants in each condition. So let's say we do this for our ANOVA that we just did. Here's the formula. The MS within that we got from our original ANOVA was 1.33, and we had 5 people in each group. So first, we'll find the column based on the number of conditions that we had in our original ANOVA. We had 3 conditions in our original ANOVA. So that was no video, live action video, and VTuber. So we're in the column labeled 3. And then we go to the row based on the degrees of freedom of our error term, our degrees of freedom within. Our degrees of freedom for our error term was 12. So we're going to the row labeled 12. And then you'll see there's 2 numbers where those meet. So we see 2 numbers here. That's not a problem. Let's look up here. The critical values for Q corresponding to alpha of 0.05 are light face. In other words, they're not bolded. 0.01 is the bolded ones. So we want the light face font. We want this top one, this 3.77. So Q is 3.77 here. We plug that into our formula. 3.77 times the square root of 1.33 divided by 5. Solve through that. Your HSD value is 1.94. What this means is that any difference between 2 conditions, so any difference between the means of 2 conditions that is bigger than 1.94 is significant according to the Tukey test. You would reject the null. So just as a reminder, the difference between the no video condition had a mean of 1. Yeah, I'd never heard light face until I started dealing with these these tables either. But apparently light face is the opposite of bold. Anyway, so the mean of the no video condition is 1. The mean of the live action video condition is 4. The difference between 4 and 1 is 3. So 4 minus 1 is 3. 3 is bigger than our HSD value of 1.94. So we would reject the null. We would conclude that there is a significant difference between these 2 groups. That's how Tukey tests work. Yeah. Now I'm wondering, is light face only used in this particular series of tables, or is that like a... No. The Oxford English Dictionary and Merriam-Webster, they all have Definitions for light face. Yeah, I just never encountered that term until I started looking at these tables, and they're like the light face type versus the bold face type. And I'm like, oh, okay. There you go. Merriam-Webster says light face is a typeface having comparatively light, thin lines. Mm-hmm. The more you know. The more you know. Anyway. So in terms of like how conservative these things are, the least conservative follow-up test you can do is a planned contrast. Planned contrast, it's easiest to reject the null of planned contrast, but that also means you're more likely to get a type 1 error. Second most conservative is Tukey. Tukey, it's harder to reject the null with the Tukey test than a planned contrast, but it's easier than with Chaffee, and then Chaffee is the most conservative of the three that we talked about. Next week, we're going to talk about Bonferroni corrections. Those are the most conservative of any follow-up test we'll talk about. And that's why people don't like Bonferroni corrections. Like, we like some degree of controlling for type 1 errors, but some people think Bonferroni corrections go too far, which I think is funny, honestly. It's funny how vitriolic people get about Bonferroni corrections. I honestly don't get the hate. Oh, you recognize that one? That actually surprises me, because they're not very popular in psychology. So, but maybe they're more popular in biology. That said, I've used Bonferroni corrections before, and I will use Bonferroni corrections again. At least when I was taking genetics, that was the one that was always used. That's really interesting. That's really interesting. Like, I submitted a paper that used a Bonferroni correction to correct for type 1 error, and the reviewers were like, why did you use a Bonferroni correction? That's too conservative. You're being too careful here. You shouldn't have used that. Like, they were suspicious of us because we'd used a Bonferroni correction. Because genome-wide association stuff had omega high n, so omega high sample sizes. Yeah, at that point, you probably don't need to be as worried about using a Bonferroni test because your error is so small that your test statistics are going to be so big anyway. You're probably going to be rejecting the null no matter what. Of course, that also, at that point, actually, it makes sense to use a very, very severe correction in that situation. It makes sense to use Bonferroni in that situation if you have such a huge sample size, because you also got to worry about the crud factor. I guess I'll talk about the crud factor in a later lecture, but why don't we talk about the crud factor now, as long as we're at it? Today you learned, yeah. Okay, so the crud factor. The crud factor is a technical term. It's a technical statistical term. I suddenly feel the need to check if other, so the crud factor is commonly used in psychology, it seems like. I'm not sure if they would have used this in, like, if you would have heard this in biology, but it looks like social sciences. We were told to do the Bonferroni anytime we were doing GWA stuff, so I'm happy to learn that there's a decent reason for yeah, there's absolutely a decent reason for that, and part of that reason is the crud factor. So the crud factor is that once you get a big enough sample size, you have so little, your estimate of sampling error becomes so small and your critical value becomes so small that you will find differences or find relationships between anything. So like, behavioral and psychological science started encountering this problem a lot when we started working with giant data sets from the internet. Like there was a while where some psychologists had access to data from Facebook, and so they had millions and millions and millions of data points, and they were running correlations between these things. And they were finding correlations between completely variables that had no reason to be related, like stuff like the number of friends like people from one particular town had on their account, and the number of, I don't know, the number of eggs sold in Canada that day, or something. Like, they were finding these significant correlations. They were rejecting the null on these correlations between variables that had no business being correlated whatsoever, and the correlations were teeny tiny. They were less than 0.1. They were very, very, very small correlations. These variables had no reason to be correlated with one another, like no theoretical reasons or anything like that. But they were still getting all these significant correlations. And the problem there is that once you get a big enough sample size, once you get a big enough N, you have so little sampling error and your critical value to reject the null is so small that you will find anything you want to. So like there's kind of a sweet spot when you're, and this is like especially a problem with correlation, but I think to an extent it can probably be a problem with other types of hypothesis testing as well, maybe, but I think correlation is where it's especially bad. So if you get a really, really, really big sample size, whether especially a correlation is significant or not becomes much less important than how strong the correlation is, because anything will be significant. Once you get into like the thousands or tens of thousands or hundreds of thousands or millions of data points, you're no longer paying attention to your p-value, because at that point it doesn't really mean anything. You're paying attention to how strong the correlation is. And like it sounds like if you have a very, very, very high N in like genome research or something like that, it might not, depending on the type of test you're doing, if you're doing like a t-test or something, you might not have to worry about the crud factor quite as much, but because your sample size is so big, it's going to make your sampling error look so small that you do want to be extra cautious, and you might want to use a Bonferroni correction there for sure. Do dimensionality reduction techniques factor in here somehow? Unfortunately, I don't actually know enough about that to say, but if we're talking about like dimensionality reduction techniques like the type that's used in like machine learning or cluster analysis or factor analysis, it's entirely possible. And so that's why I think that's one of the reasons like when cluster analysis and dimensionality reduction, you have a threshold for how much of the variability has to be explained for one of those clusters for you to actually keep that cluster. Because at a point, you are going to find clusters of variables that are correlated with one another. But there's a point where those correlations are so small and they're not explaining anything to the point where they're actually useless. So I do imagine that this is related to that, and that is also why in dimensionality reduction techniques we have things like eigenvalues and stuff, or like we choose specifically, we are going to pick like clusters that explain up to X% of the variance. Like we'll pick the first few clusters until we've explained like 90% of the variance, and anything that explains less than that we don't care about, because it could be meaningful, but if it's not explaining much, it's not useful, and maybe it's not even meaningful. So yeah, like I don't know enough to say for sure, Marlon, whether these things are directly related, but I think it makes a lot of logical sense that the crud factor would play into at least the type of dimensionality reduction techniques that I'm familiar with. Did that answer your question at all? I know that, like, again, I'm not an expert enough to give you a really good answer, but oh, good. Oh, good. Yeah, that's something interesting to look into. It kind of has me thinking about, like, I did some machine learning for a while, and it kind of has me thinking about the whole black box thing, you know, like you'll train a machine learning model to say classify these things. You'll train a classifier to like look at an image and say, does this image contain a cat, yes or no, or whatever. And a lot of the time, these machine learning algorithms, we can't see what dimensions or what features of the image they're using to make that decision. And sometimes if we can extract the features. Like I would sometimes create a machine learning model to like classify text, and then I'd extract the features it was using to classify text. And sometimes it was really obvious what that feature was. Like, oh, this type of text contains more URLs than that type of text. But other times I could not tell what it was picking up on. And maybe that was some crud factor, or maybe it was something that the computer noticed was highly predictive, but the human brain could not understand the pattern there or something. I don't know. I'm sorry, that's always been in the back of my mind for a while. I always think it's interesting that like machine learning and models and classifiers can pick up on patterns that humans cannot pick up on and humans cannot even interpret. It's so interesting to me. And like whether that pattern is actually a meaningful pattern or whether it's an artifact of the way that the data was collected that was fed into the model or something. I do wonder what ways abstract patterns are present in ways we don't have an intuition for. Right? It's such an interesting problem. That stuff has always fascinated me. Like ever since I learned about like these strange things that classifying models do, it's just so interesting that they're picking up on these patterns that sometimes humans can look at the pattern and they're like, oh shoot, I never thought that would be important, but the computer picked this up and I know what it's telling me. But there's a lot of other times when the computer picks up some sort of distinct identifying difference between these two sets of things. And even if you see all the things that the computer's looking at, here are all the words the computer's using, or here's all the punctuation or typographical features, the human brain simply cannot make sense of what rule the computer is using. Like, why are these things meaningful? And why do these things hang together? Here, human, here's your daily rock to eat for your health. Oh man, when I'm talking about ChatGPT and like AI and stuff in my classes and trying to encourage my students not to use it because it's not necessarily accurate, especially like the Google one, one of the things I show them is Googling, do I have to fight a snake to graduate? Because of that one McSweeney's article. Do I have to fight a snake to graduate? And you Google that, and Google AI says, oh no, they fixed it. They fixed it. They fixed it. Now the Google AI recognizes that that was satire. But back when I was looking at it, Google AI did not recognize that that McSweeney's article was satire. It just took it as fact that some people had to fight snakes to graduate from graduate school. They usually spot treat the silly cases that make rounds on. I made sure that that one didn't make rounds on social media. Like I only showed it to my students. I didn't show it to anyone else. And I came up with it myself and found it myself, but it's possible that somebody else did end up finding it. Or maybe because there's only one source saying it and it's McSweeney's, maybe they were able to say, hey, information from this source should be flagged as satire and treated as such. It's possible they were able to update the model to do that. Or maybe, yeah, maybe somebody else caught it and reported it to them. That's a bummer, though. No, wait! Oh, never mind. Nah, yeah, that's a bummer. Anyway. Okay, I've got some review slides. Or, well, a review slide. Been doing raids for the last hour and only just got another Herba Mystica. I'm so sorry. You're not having great luck today, are you? Maybe? I'm so sorry. The students who used ChatGPT got killed by mistake. According to the McSweeney's article, I bet, like, when the McSweeney's article came out, if any of you are not familiar with the article that I'm talking about, I'm going to link it in chat, if chat will let me. But according to the McSweeney's article, based on the principles laid out in it, I imagine that if you were caught using ChatGPT, or like you were strongly suspected of using ChatGPT in this alternate universe where you have to fight a snake during your defense, it would be a poisonous snake. Because they do say, I think it's like, the quality of your work determines which snake you will fight. The better your thesis is, the smaller the snake will be. So you'd probably get a very big snake if they thought you used AI to write your thesis, I imagine. Where's the... I thought I remembered something about poison in there. If you get a poisonous snake, it often means there's a problem with the formatting of your bibliography. And you know what AI is notoriously infamous for? Making up stuff in the bibliography. So I assume, extrapolating from the McSweeney's article, that if you used AI to write your thesis and then defended it in this universe, you would get a very large poisonous snake. Very Egyptian afterlife core. Can you bring a weapon or do you have to do it with your hands? That's in part of the FAQ, I think. Let me see. I don't think, actually, no, it doesn't say anything. I could have sworn they said something about having a weapon. Oh yeah, so the first question is, do I have to kill the snake? University guidelines state that you have to defeat the snake. There are many ways to accomplish this. Lots of students choose to wrestle. Some construct decoys and elaborate traps to confuse and then ensnare the snake. One student brought a flute and played a song to lull the snake to sleep. Then he threw the snake out the window. So it seems like direct weapons aren't necessarily allowed, but clever things like traps and decoys and playing your flute is allowed. Though, of course, this isn't a be-all, end-all FAQ. I wonder if they've done an updated version of this article. I love this article so much. Highly recommended. Very short as well. Short read, fun read. Anyway, review. Okay. First question. When would I use a planned contrast instead of a post hoc test? Or when would I use a how would I decide between a planned contrast versus a post hoc test? Co-host put out a lot of AI decoys while it was still around. Oh no. If it's just defeat, can I just like challenge it to who cannot be a snake and win by default? Perhaps, perhaps. That's not in the FAQ, so I can't say for sure, but that does sound like it's potentially a way to do it. That said, the snake is released while you're defending, if my memory is correct, and therefore, yeah, the snake is lurking. So the snake fight generally starts after you finish answering questions, but the snake will be lurking in the room the whole time and it can strike at any point. If the snake attacks prematurely, it's obviously better to defeat it and get back to your defense as quickly as possible. So I assume that that kind of challenge wouldn't necessarily stop the snake from attacking you. I think by defeat, they probably mean prevent it from attacking you one way or another. Anyway, yeah, so when would I use a planned contrast versus a post hoc test? Or what is the deciding factor for which one I would use? Plan when we have a strong contrast, post hoc when not that? Yeah, strong hypothesis, I think. Yeah, I got you. I got you. Yeah. I do stuff like that all the time. It's like I have a word in my head and it just makes its way into the sentence, whether it should be there or not. But yeah, when we have a strong hypothesis, you do a planned contrast. If not, do a post hoc. Though frankly, current norms in psychology are just like, just do a post hoc. Just do the post hoc, whatever. What is experiment-wise error? Can anyone remind me what experiment-wise error means? Total error across all measurements, correct. The total probability of making a type 1 error across all of the tests you do. Good job, Hairday. All right, one more. There are many correct answers to this question. There's a lot of potential correct answers to this question, but can anyone tell me how we can protect against a type 1 error, a false positive, when doing multiple comparisons? In other words, when doing multiple hypothesis tests, or comparing more than two groups. Multiple answers, I'll take any one of the correct answers. I'll also take incorrect answers, because that will help me explain things. Maybe. Use a stricter test. Yes, exactly, Hairday. We can use a stricter test. So that could mean using a post hoc test instead of a planned contrast. That helps us protect against type 1 error. Another way is just use an ANOVA instead of a bunch of t-tests, right? Start with an ANOVA. If the ANOVA is significant, then you can go on. If it's not significant, stop. Yeah. That's the last slide I have for today. Any questions, comments, anything like that, clarifications, anything I can do for y'all? Like, I'm done for now. I have no more slides for today. I mean, if not, that's okay too. I'm okay with that. Can save up my voice for tomorrow. Oh my gosh, I've talked so much this week. I've enjoyed every second of it. Don't get me wrong. I love talking to y'all. I'm just nice. I was grabbing some water. What was the question? The question was just anything else y'all want to ask before we end class, or anything you want to say or whatever. Yeah. Yeah. I'm gonna make myself a hot chocolate and play some Minecraft. Yum. Yeah, I'm excited. I've got some like some peppermint bits to put in the hot chocolate. Mmm. Oh, I wish I could get vanilla hot chocolate. I had white hot chocolate and it was so good. But no, just normal hot chocolate, and then I'm gonna put some peppermint in there. Very excited about it. It's very yummy. 10 out of 10. I think I'm out of whipped cream though, which kind of stinks, but oh well. Anyway, all right, I guess that's it. Good night, everyone. Thank you so much for coming. I hope that you have a great day. Take care of yourselves. Get some good sleep when it is time for you to do so. All that good stuff. I've had white hot chocolate and it was heavenly, but it looked so much like sick. Oh gosh, I guess the one time I had white hot chocolate, it was in a closed cup where I couldn't see it, so maybe I was lucky. I salute you too, Phi. Maybe if I make another live 2D model for myself, I should give it a saluting toggle because I feel like I do that a lot. The sheer amount that I use the saluting emote is a lot. All right, wow. All right. Take care, everyone. It was, oh, thank you. I like it. It's my comfy, comfy poncho. I accidentally screwed something up on it, but, oh wait, no, it's still there. But if you can't see it, that's okay. I like it. It's comfy. All right. Thank you. Thank you. Take care, everyone. Have a great day, night, thing.